Explain denormalization and when it might be useful. Denormalization is a database design technique that involves intentionally introducing redundancy into a relational database by combining data of multiple tables into a single table or duplicating data in multiple tables. This approach is opposite to normalization, which aims to eliminate redundancy and improve data integrity. Denormalization can be useful in specific scenarios where performance or query simplicity outweighs the benefits of normalization. Here is an explanation of denormalization and when it might be useful. Use case for denormalization. Improve query performance. One of the primary reasons for denormalization is to enhance query performance. By combining data from multiple related tables into a single table, you can reduce the need of complex join, leading to a faster query execution. Aggregation and reporting. In reporting and analytics databases, it's common to use denormalization to create data warehouse or data marts that simplify complex reporting and analytical queries. Denormalization structure can make it easier to perform aggregation and calculation, reduces join. In high transactional databases, frequent joins can impact performance. Denormalization can help to reduce the number of joins required for common queries, speeding up the data retrieval. Caching. Denormalization can be useful for creating pre-computed or cache view of data. This can improve response time for frequently accessed queries because the data is readily available, reducing the need to perform complex join. Offline processing. In scenario where data is primarily used for batch processing or offline analytics, denormalization can simplify data preparation and reducing the time required for data processing. Distributed databases. In distributed or no SQL databases, data is often denormalized to improve the data locality and minimize network traffic. This can be beneficial for distributed systems where joining data across network nodes can be costly. Trade-off and consideration. While denormalization can offer performance benefit, in certain situations it comes with a trade-off and considerations. Data integrity. Denormalization can potentially lead to data integrity issues because redundant data can become inconsistent if not properly maintained. Updates, inserts, and delete need to be carefully managed to prevent anomalies. Managing complexity. Denormalized database can be more complex to maintain, especially when updates to a data structure are required. Careful attention must be paid in keeping the denormalized data in sync. Storage requirements. Denormalization can lead to increased storage requirement due to data duplication. This may be concern for large data sets. Query complexity. While denormalization can simplify some queries, it can complicate other. It's important to consider the type of query the database will support and how denormalization will impact those queries. Reporting versus OLTP. Denormalization is often more suitable for reporting or analytical databases than online transactional processing systems. It's important to choose the appropriate design based on the system primary use case. In summary, denormalization is a technique that involves introducing redundancy into a database to improve query performance and simplify data retrieval. It is most useful in scenario where query performance is higher priority than the data integrity and where trade-offs are well understood and managed. Carefully planning and maintenance are essential when denormalizing a database to ensure that the data remains consistent and reliable.